Hello everyone, welcome to week 5 pattern recognition and application problem solving session. I am Tanuka Bhattacharjee from IISc and I am a PhD student over there in the electrical engineering department. So as we are doing these problem solving sessions, in the last week we solved problems on parametric estimation of probability density functions. Mainly we worked with maximum likelihood estimation. In today's session we will move to the non-parametric estimation of probability density functions and some methods of that, the methods that you have studied in this week's sessions. So let us get started with the first problem. So as you see, the first problem says, which of the following is or are true in relation to non-parametric PDF estimation? The first statement is that non-parametric PDF estimation is used when we have very few samples, and it is also used when analytical expression of underlying PDF is not known. And we have to say which one of them or both of them or none of them is true in relation to non-parametric PDF estimation. So guys, any of you would like to answer which among these two statements are correct for non-parametric PDF estimation? Anyone? You can just post it on the chat. Any idea, guys? You can just put your idea, whatever you think. Okay, I don't see any response in the chat box. Okay, I'll explain this. So here both the statements are true in case of non-parametric PDF estimation. So the first statement says that it is used when we have very few samples. So if you have very few samples, then it is very difficult to correctly estimate any parameters. Even if you know what particular parametric form the PDF is having, still in order to estimate those parameters, if you have very few samples, then your estimates should be erroneous. So in spite of knowing the parametric form with very few samples, its accurate estimation is not possible. So you will have to go for non-parametric estimation in case of the situation where you have very few training samples available with you. And the other statement says that it is also used when analytical expression of the PDF is not known. So if you do not know the analytical expression or the particular parametric form that the PDF is having, then of course you do not know which parameters are there to estimate. So there is no question of using any parametric PDF estimation technique, because you don't know which parameter you need to estimate, what exact form that PDF has. So you will obviously have to go with the non-parametric estimation. So in both cases, if you have very few samples, you cannot estimate parameters perfectly, then you have to go for non-parametric. As well as if you have samples but you do not know what is the expression for the PDF that these samples are taken from, then you do not know the parameters to estimate and you have to go for non-parametric PDF estimation. So in this case, both option 1 and 2 are correct in context with the non-parametric PDF estimation. Okay. Now let us proceed to the next problem. This problem is on histogram based PDF estimation technique. So it is said that in histogram based PDF estimation technique, let Wj represent the width of the jth interval, n represent total number of samples, and nj represent the number of samples which fall within the jth interval. Then we are asked to compute the height of the jth interval. So here the situation, if I draw it, let's say we represent the variable for which you are estimating this PDF with as x. So my x axis I am representing as x, and y axis is the PDF estimate px or p hat x, because it is an estimate, it is not the actual PDF. So we are going to have the histogram based PDF estimation. So this p hat x is the histogram based PDF of the variable x. So let's say the range of x lies within this. So this is the x mean and this is the x max. So x can assume any value within this interval. Now for histogram based PDF estimation, what we do is we divide this entire range into some intervals of equal length. Let's say this is the jth interval. This one is the jth interval. So it is said that Wj is the width of the jth interval. So this width you have is Wj, and capital N is the total number of samples that you have, and among these total capital N number of samples, Nj samples fall within this particular jth interval. So you have Nj number of samples in this interval. So the fraction of the total number of samples which fall within this jth interval is Nj by n, or this is the probability that a sample will fall within this particular interval. Now the point is, we are using histogram based PDF estimation for estimating or approximating a continuous PDF function. So the area under a continuous PDF function is always 1. So in case of this histogram based estimation, the area under this histogram based PDF estimation should also be 1. So let's say at jth bin, let's say the PDF estimate is like this. Similarly, you will have PDF estimates at each bin. So the sum of the area of all these corresponding to all these intervals, so sum of all these areas should be equal to 1, because we are trying to approximate a continuous PDF function. So the area at each interval has to be, if we sum the area at each interval, then it has to go to 1. Now if you see this fraction, this Nj by n, which is the fraction of samples which is falling within the jth interval, if you sum this number Nj by n, Nj by n over all values of j, you will get 1. So if you can make the area corresponding to each interval or area corresponding to jth interval equal to Nj by n, then if you sum all these areas, it will be equal to 1. So we have to make the area of the jth interval equal to Nj by n. Now we already know that the width of this box, this interval is Wj. Let's say the height is Hj. So Hj is the height. So the area will be Wj into Hj, height into width, and this you will have to make equal to Nj by n. Then if you sum over all the areas of all the intervals, you will get the sum as 1. So, if you have this, then you can easily calculate 8j. 8j will be nj by capital N into wj. So, or write it a bit more clearly. Nj by N into wj. So, this will be the height of the jth interval. Like that, you can estimate the height of any interval based on the fraction of the samples that is falling within that interval. You can estimate the height of that particular interval. So, this is how you estimate the height of any interval in case of histogram based PDF estimation technique. Guys, if you have any doubts at any point, you can post it in the chat. Okay. Now, let us move on to the next problem. So, here in the third problem, it is said that suppose we have 10 sample values. These are the 10 training sample values that you have been given, 1.1, 2.1, 2.5, like that you have 10 sample values. Now, the first question is determine the probability density for the given samples using histogram based PDF estimation technique with bean width wj equal to 1. So, you will have to use histogram based PDF estimation technique, and you will have to use the bean width wj equal to 1. And you have already seen how you can estimate the height corresponding to each bin or each interval. So, we can now easily calculate this PDF. So, let us do that. So, as you see in the question, all the sample values that you have, the first sample value is 1.1 and the last one is 4.7. So, you can say all the values lie within 1 and 5. All the samples are greater than 1 and less than 5. So, we can safely take the range of the sample values as 1 to 5. I'll represent the samples by x. So, if I draw it, x axis is x. So, I have the range of x from 1 to 5. Now, I'll have to divide this entire range into intervals of equal width, and I have been given that the width should be equal to 1, because in the question it is said that the bean width wj is equal to 1. So, all the bean width should be 1. So, if you have 1, then the first bean will be 1 to 2, 2 to 3, 3 to 4, 4 to 5. Like that you will have 5 from 1 to 5, the entire range you will divide it into a number of 4 bins. Okay, this is our axis of p hat x. Now, let me write down the sample values on the next page. 1.1, 2.1, 2.5. Have 1.1, 2.1, 2.5, then 3.1, 3.3, 3.6, 3.8, 3.9, 3.8, 3.9, 4.5, 4.7. These are the 10 values. sample values. So let us first take the first bean from 1 to 2. So we have to check how many samples fall within this interval. So as you can see, only the first one, 1.1, falls within the interval of 1 to 2. So you have only one sample in this interval. Now the next interval is 2 to 3. So you can see 2.1 and 2.5 both fall within the interval of 2 to 3. So we have two values within the range 2 to 3. So number of samples in this interval is 2. Then the next interval is 3 to 4. So here we have 3.1, 3.3, 3.6, 3.8, 3.9. So total we have 5 samples within this particular interval 3 to 4. 5 sample values are falling within this range. Now the last interval is 4 to 5. So as you can see, 4.5 and 4.7 are lying within the range of 4 to 5. So in this last interval, the number of samples present is 2. Okay. So if you take any interval as nj, for j equal to 1 to 4 here, so the value of nj, which is the number of samples falling in the jth interval, is 1, 2, 5 and 2. So now you will have to estimate the height at each interval. So as we calculated in our previous problem, in this one, this height will be nj by capital N into wj. Okay. So the expression for height is hj equal to nj by capital N into wj, where nj is the number of samples falling in the jth interval, capital N is the total number of samples available, and wj is the width of the jth interval. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 samples given. So here the total number of samples, capital N, is 10. And we have taken wj equal to the bean width, that is 1 for all the beans. So this is 1. So your hj, if you put these values, this simply becomes nj by 10 into 1, which is 10. Nj by 10 will be the height at each interval. And the numbers that I wrote on the axis 1, 2, 5, 2, these are basically the nj values corresponding to the intervals. So if we divide this value by 10, that gives us the height of each interval. So the height of the first interval will be 1 by 10, that is 0.1. Let's say this is the height. And as you know, in case of histogram based PDF estimation, you assume that the PDF is constant within the interval. It is like piecewise linear. So at each interval it is constant. It changes from interval to interval. So first interval, the value is 0.1. In the next interval, nj is 2. So hj will be 2 by 10, that is 0.2. This is, let's say, 0.2, this is 0.1. For the next interval, nj is 5. So hj will be 5 by 10, that is 0.5. Somewhere here. This is 0.5. Then in the last interval, 4 to 5, you again have nj equal to 2. So your hj will be 2 by 10, that is 0.2. Now if we simply join this, this is our final estimate of the PDF. This card. This gives us the histogram based estimation of this particular PDF. Okay. Now, let us move on to the next part of the question. Okay, before that, let us check one thing. So, we said that we want to make the area under the PDF equal to 1 in order to make it equivalent to a continuous PDF, or to make it approximate a continuous PDF, we want to make the area under the PDF as 1. So, here let us compute that. So, here the width of each interval, this width is 1. So, if you want to compute the area corresponding to the intervals, each interval, you just need to take the height, because width is already 1. So, your area will be equal to height. So, if you sum the heights over all these intervals, you should get 1. Let us check that. So, for the first interval, the height is 0.1 plus the next interval is 0.2, so 0.3, plus the next interval is 0.5, so 0.3 plus 0.5, 0.8. Last interval is again 0.2, so 0.8 plus 0.2, 1. So, it matches. So, it estimates a PDF only. Now, let us move on to the next part. The next part is find the probability density at location 4.5. 4.5 is somewhere here. You have to find the probability density at this point. This will basically be the height of this PDF at that particular point, or here at 4.5, whatever is your height of the PDF, that will give you the estimate of the probability density at that particular point. So, basically if you consider the height at this point, so this will be the estimate of your probability density at 4.5. So, you can see that is equal to 0.2. So, the probability density value at x equal to 4.5 is equal to 0.2. Okay. Now, in the third subpart of this problem, it is said that repeat with Wj equal to 2 and Wj equal to 0.5. This is to see what is the effect of having different bean widths on the estimation of the PDF. So, let us first take Wj equal to 2. Okay. Wj equal to 2, or the bean width is equal to 2. Now, your entire interval is 1 to 5, entire range is 1 to 5. So, the first bean, if you take the bean width as 2, then the first bean will be from 1 to 3 and the next bean will be from 3 to 5. So, you will have only 2 beans in this case. So, in this case, we have one bean as 1 to 3 and the next bean as 3 to 5. You have only 2 beans, and this axis is again p hat of x. So, to determine the PDF histogram, you have to first check how many samples lie in each interval. So, let us take the first interval, which is 1 to 3. So, we will have to check how many samples lie within 1 and 3. So, you can see 1.1, 2.1 and 2.5. 3 values lie within the range 1 to 3. Here we have 3 values, and remaining all are greater than 3 and less than 5. So, remaining all will lie within the range 3 to 5. So, we have 7 values in this interval. So, Nj is 3 for the first interval, j equal to 1, and 7 for the second interval, or j equal to 2. Now, here your Wj is 2. So, here a capital N is again 10 because you have 10 samples. Wj is 2 in this case. So, your Hj will now be Nj by 10 into 2, that is 20. Now, your height in each interval will be Nj by 20. So, in the first interval, that is the 1 to 3 interval, the height will be here Nj equal to 3. So, the height will be 3 by 20. Let us say that is somewhere here. This is 3 by 20. And in the next interval, 3 to 5 interval, the Nj value is 7. So, here your Hj or height in this interval will be Nj by 20, that is 7 by 20. Let us say somewhere here. So, this will be your PDF estimate. This is basically 7 by 20. This will be your PDF estimate in this case. Now, here also you can verify that the area under the PDF is 1. For that, here each interval width is 2. For the first interval, height is 3 by 20. So, the area will be 3 by 20 into 2, plus in the second interval, the height is 7 by 20 and width is again 2. So, the area will be 7 by 20 into 2. That basically becomes 3 by 10 plus 7 by 10, which is equal to 1. So, again you can see that the area under the PDF has come up to 1. Now, again let us take the same point x equal to 4.5 and try to estimate the PDF value at that point. So, at 4.5, which is somewhere here, the height is this, that is 7 by 20. So, the PDF value at this point will be 7 by 20. So, P of, or we can say P hat of x equal to 4.5 is 7 by 20. As you can see, when you used the beam width as 1 and when you use the beam width as 2, the probability density estimates that you got for the point 4.5 is different. And if you see the two PDFs, you can also see that when you had Wj equal to 1, you had more detailed structure. There were a step from 1 to 2, first interval to second interval, then another step from second to third, another going down from third to fourth. All these details were there. But when you made your width equal to 2, you just have 2 bins and there is just 2 levels in the PDF. You have lost those detailed information. So, the message is, if you use 2 wide intervals, then you will lose the detailed information. But if you now make the intervals too small, that is also not a good idea. Let us see why. We will take Wj equals to 0.5, which was the last part of our question. So, now if you have Wj equals to 0.5, then this is your axis again, this is x, your range is 1 to 5, but now you will have the beans of width 0.5. So, your first bean will be from 1 to 1.5. So, 1 to 1.5 will be 1 bean, then 1.5 to 2, 2 to 2.5, 2.5 to 3, like that you will have the bins, and this is 5. So, these are the bins you will have. I didn't mark all the points on the x axis, that will make it very clumsy, so I have just put 1, 2, 3, 4 and 5, but the tick marks between 1 and 2 corresponds to 1.5. So here again you will have to see how many samples fall in each interval. So the first interval is 1 to 1.5. So you can see within 1 to 1.5 only this sample value 1.1 goes within that range. So here you have one sample. Now from 1.5 to 2, 1.5 to 2 you have no samples at all, because the next sample is 2.1. So in this interval your number of samples is 0. Next 2 to 2.5. 2 to 2.5 you have 2.1. So as we know, if we have a sample value which is equal to the boundary of the bins, here for example you have one sample at 2.5 and 2.5 is your bin boundary, then you put this particular sample to that interval which is on the right side of this boundary. So 2.5 will go to the interval 2.5 to 3, not the left one, 2 to 2.5, it will not go there, it will go to the interval 2.5 to 3. So in the interval 2 to 2.5 you will only have the value 2.1. So you have one sample here. Now 2.5 to 3 you have one more sample, 2.5. Now 3 to 3.5, here you have two samples, 3.1 and 3.3. Then 3.5 to 4, here you have three samples, 3.6, 3.8, 3.9. Three samples over here. And 4 to 4.5, again you have no samples, because 4.5 will go to the interval 4.5 to 5. So you have no sample in the interval 4 to 4.5, and in the interval 4.5 to 5 you have these two samples, 4.5 and 4.7. So here you have no samples, here you have two samples. Now in this case also we will similarly estimate the heights of each interval. So our capital N is 10 as before, and Wj is 0.5. So your Hj is Nj by N into Wj, that will be equal to Nj by 5. Okay, that will be your height. So if we draw it, in the first interval the height will be 1 by 5, then it will be 0, again 1 by 5, 1 by 5, so this is the 1 by 5 level. Then you have 2 by 5, then you have 3 by 5, so this is 2 by 5 and this is 3 by 5. Again you have 0, and the last interval you have 2 by 5. So if you join these, this is the PDF that you have. This is the PDF estimate that you have. Here also you can check yourself that the area under the curve will equal to 1. Now here if you want to compute the probability at 4.5, or what was the point? Yeah, 4.5. At 4.5 here your height is 2.5. So the probability density at 4.5 will be 2 by 5. So you see in all the three cases you got different values of the probability estimate. Now in this case you see you have taken very small intervals and you have ended up with bins with no samples at all. So this particular interval and this particular interval you didn't have any samples, so you have made the probability density estimate for that interval as 0. Now if you if you try to estimate the probability of any point in these intervals, let's say at 4.3, if you want to estimate the probability density, that will always be 0. Okay, so you have made two fine divisions so that you have ended with empty bins. Okay, so the message is you should choose the width in an optimal way. It should not be too large, then you will lose the detailed information, and it should not be too small so that you end up with empty bins. Okay. Okay. So this was about histogram based PDF estimation. Now there are other methods of non-parametric PDF estimation, which is called the window based technique or kernel based technique. Now we will look into that. So the first problem is, suppose we have 10 sample values given this. These are the 10 sample values we have. Now determine the probability density for the given samples using rectangular window based PDF estimation technique, and your base width will be W equals to 2. So now you have to use rectangular window based PDF estimation. So as you know, in case of window based PDF estimation or kernel based PDF estimation, what we do is we take a representative PDF function or window function and we put that window function at each sample value. So as many samples as you have, at all those points you put your chosen window function, and if you then take the sum, that will be your PDF estimate. So here you have been told that you have to use the rectangular window. So how does that look like? As we know, rectangular window is something like this. If the middle point is x, let's say the middle point is x, then this is the width of your rectangular window. Here you have been told that your width is 2, W equals to 2. So towards right of x you will have half of the width, and towards left you will have half of the width. So on each side this interval will be equals to half of W, that will be equal to 1. So this point, this right hand side edge will be at x plus 1 and the left hand side edge will be at x minus 1. So you will have your windows like this. Now this is about the width. Now you have to compute what will be your height of the window. Then you can completely describe the window. So in this case also, since we are trying to estimate continuous PDF, we will have to make the sum of the area under the entire PDF equals to 1. Now here the point is at each sample value you are putting the same window function. So at each sample value the area under this window function is equal. Now here you have 10 sample values. If the area of each window is, let's say A, let's say the area of each window is A. Now you have put this particular window at 10 different locations. If you have, let's say, one sample value occurring 2 times, then you will place that same window twice at that point. So you have 10 windows each of area A. So the total area will be 10A, and that you need to make equal to 1. So area of each window will be 1 by 10. Basically it is 1 by capital N, 1 by the number of sample values. That will be the area of this rectangular function, rectangular window function. Now, so if you denote the height by h, the area A is basically equal to W into h. Here your W is 2, so 2h, and that should be equal to 1 by 10, right? So your h should be equal to 1 by 20. So, the height of each rectangular window should be 1 by 20 and width is 2. Now, you will have to put such windows at each sample point and take the sum, that will give you the PDF estimation. So, if you have the axis like this, you have the sample values starting from 1 till 7. So, your range is 1 to 7, but you will put the first window at 1. So, the middle point of the window will be placed at 1. So, the left hand side edge will go to 0 because it will go to x minus 1. So, it will go to 0, and the window that you will put on 7, the right hand side edge of that window will go to 8 plus 1. So, your entire range should be 0 to 8. 1, 2, 3, 4, 5, 6, 7, 8. Now, the first sample is at 1. So, the first window you will have to put at 1. So, at 1 you will have one window. This is the window. Next, you have the value 2 times. So, you will have to put 2 windows at the point 2. So, at 2 you will put 2 windows, 1 window, 2 window. 2 windows you will put at 2. Then next you have 3, 4, 5 each one time. So, you will put 1 window at 3, which will range from 2 to 4, 1 window at 5, 1 window at 4, which will range from 3 to 5, and 1 window at 5, which will range from 4 to 6. Then you have the sample value 6 3 times. So, you will have to put the window 3 times at the point 6. So, at 6 you will have 3 windows, 1, 2 and 3. 3 windows at 6. So, these will span from 5 to 7, and the last window is at 7. So, it will span from 6 to 8. Now, if you sum all these windows up, you will get the PDF. So, this height of the window is 1 by 20, right? This is 1 by 20. So, if you sum it, here you have 1 by 20, then you have 3 windows. So, the height will become 3 by 20 here. This is 3 by 20. From 2 to 3 also you have 3 windows. So, again you will have 3 by 20 height. Now, 3 to 4 you have 2 windows, 4 to 5 you have 2 windows. So, your height will be, each window is 1 by 20, so 2 by 20, somewhere here. Then in 5 to 6 interval you have 4 windows. So, the height there will become 4 by 20, somewhere here. Next also you have 4 windows, and in the last you have 1 window, so 1 by 20. Now, if you join this yellow line is your final estimate of the PDF function. This is your final PDF estimate using the rectangular window based PDF estimation technique, and this is basically 4 by 20, this is 3 by 20, this is 2 by 20. Okay. Here also you can sum the area under the curve and you can see that will amount to 1. Now the next question is find the probability density at location 3.5. So your location 3.5 is over here. Location 3.5 is over here. You can estimate the probability density at this point by two ways. One, you can take the height at that particular point directly, which in this case is basically this height. This is 3.5, you have to take the height of the PDF function at that point. Here that is 2 by 20. So you can directly tell that your p hat x equal to 3.5 is 2 by 20 or 1 by 10, that is 0.1. The probability density value at 3.5 is 0.1. And another method is you put one window at the test point. So at 3.5, you put a window. So that will span like this from 2.5 to 4.5. This will span like this. My drawing is not that accurate here. This window will span like this. Now you need to see what all training samples fall within this window, within 2.5 to 4.5. So here you see within 2.5 to 4.5 you have two values, 3 and 4. So at 3 and at 4 you have two sample values. So you take the height or the value of the window function at these two points, 3 and 4. At these 2 points you take the value of this window function. So these two values. So as we know the height of this window is 1 by 20. So at each point your value will be 1 by 20. So the contribution of the training sample 3 is 1 by 20 and contribution of the sample 4 is also 1 by 20. And remaining samples do not fall within this window. So all those remaining samples do not contribute towards the PDF value at 3.5. Now if you just sum up these contributions, you will get the probability density at 3.5. So p hat x equal to 3.5 is equal to contribution from 3, which is again height 1 by 20, contribution from 4, which is again 1 by 20, and you sum up, this is again 0.1. So in both ways you can compute the probability density at any point. Okay. Now let us move on to the last problem of today's session, or last problem on non-parametric probability density estimation. So here you are again given the same 10 sample values and you have been said that use triangular window based PDF estimation technique with base width W equals to 2. You have to use triangular window and the width W will be equals to 2. So the first question is what will be the height of the triangular window used for each sample. So as we computed the height of the rectangular window, similarly we will compute the height of the triangular window. So the triangular window will look something like this. If you see this point, the middle point as x, your width is 2. So that width will be equally divided on both sides of x. So your right hand side edge will again be x plus 1, left hand side will be x minus 1. And this width W is equals to 2. Now again you need to make the area under the entire PDF equals to 1, and you will put this particular triangular window function at each sample point. So the area under this triangular window function will be added up for each sample point, and that should sum up to 1. So here you have again 10 samples. So 10 times, if you have this particular area, that it should be equal to 1, or your area of this triangle should be 1 by 10. Now if you say that the height is h, then for area of triangle the formula is half of W into h. So that will be equal to half into your W is 2 into h. So your area will be equals to h. So you have already determined that your area should be equals to 1 by 10 or 1 by the number of samples to make the entire area equals to 1. So your height will be equals to 1 by 10, because your area is equals to height and area should be 1 by 10. So your height should also be 1 by 10 or 0.1. Now the next question is, determine the probability density for the given samples. So as we have done for the rectangular window case, here the difference is only we will put triangular windows in place of rectangular windows. So you have the first sample at 1. So your first triangle you will put at 1. So it will range from 0 to 2. This will be your first triangle. Then you have the sample 2 times. So you will have to put 2 of these same windows at the sample point 2. So similarly as the rectangular window case, you will put 2 triangles at point 2. Then 3, 4, 5 single windows at each of these points. 1 at 3, 1 at 4 and 1 at 5. Each is spreading minus x minus 1 to x plus 1. So width of each triangle I am putting is 2. And after 5 you have 6 3 times. So you will put 3 triangles at the point 6. You will put 3 triangles at this point at 6. Here you have 3 triangles. And last at 7 you have 1 triangle, which is the last triangle. At 7 you have 1 more. Now the height of each of these window is 1 by 10. Each is 1 by 10. Now if you add up these windows, what you will get is actually the PDF estimation. So I'll draw a rough sketch of that. So here you will go like this. Then you will continue like this, because you have two windows going up and one going down. Then you will go down. So, this yellow curve more or less gives you the PDF estimate. So, this is the PDF estimate if you use triangular window function. Now, the last part of the question says what is the probability at location 3.3. Now, it is difficult to compute the height from this curve. So, from this particular PDF estimation. So, we will go by the second method of estimating the probability. So, we will put one window at the test point, and we will see the contribution of the training samples towards the probability of that test point. So, our test point is 3.3. So, we will put a window at 3.3. 3.3 we have one window. So, the left side will be 2.3 and this will be 4.3. So, again we will have to check what all samples come within this window, within 2.3 to 4.3. 2.3 to 4.3, again you see 3 and 4, 2 samples are there. One is 3 and one is 4. Now, you will have to compute the value of this window function at these points, and you sum these contributions up, you will get the probability at the location 3.3. For that, for computing these heights, the height at the value of the window function at 3 and 4, we will make use of the property of similar triangles. So, this height we know is 0.1 and we have to compute this height. Again, in the base wise, this distance is 0.7, 2.323, this is 0.7, and the entire this distance, let me mark it by red, this distance is 1, 2.3 to 3.3. So, if we take the ratio of the bases of these two triangles, this is one triangle and this is the other triangle. These are the two triangles that I am marking, or if I mark it by some other color, this is one triangle, yellow is the one triangle and red is the other triangle. So, if I take the ratio of the bases, the ratio will be 0.7 by 1, and we will have to take the ratio of the heights and make those equal. So, the height at 0.3, let us make that at h3 divided by 0.1. Okay. So, this is by the property of symmetrical triangles. So, you will get h3 equal to 0.07. Similarly, you will have to compute the value at this point. Here the two triangles will be this one and this one. These are the two triangles, similar triangles. This entire base is width is 1 and this width is 0.3. So, here you have 0.3 by 1, which is the ratio of the bases is equal to h4, let us say the height at 4 by 0.1. So, your h4 is 0.03. So, just to compute the probability at point 3.3, that is p at x equal to 3.3 p hat, you have to sum up the contributions of all the training samples that fall within the window placed at 3.3. So, you will have to sum up the contribution from 3 and 4. So, you will have to sum up 0.07 plus 0.03 and it will come to 0.1. So, this is the probability value or PDF value at the point 3.3. Okay. So, these were the problems for today's session. If you have any questions, please put it up in the chat. We will take 2 minutes to answer if there is any. Okay, I do not see any questions in the chat, so let us close today's session. Thank you guys for joining. We will meet again in the next week with the next set of problems. Thank you.